We are learning about the product rule for finding the derivative of the product of two functions. So if our function is defined as the product of two smaller functions, that's when we can use this product rule. So let's take a look at this first example here. Given that h at x is equal to the product of 2x minus 3 with 5x squared minus 6x plus 1, we're going to determine the derivative here. What we've done in the past with method number 1 is expand and simplify that h at x, the two polynomials, and then we just use our regular rules to find the derivative. So take a moment to do that. Just put the video on pause and try it. If you've done it, you should have gotten 10x cubed minus 27x squared plus 20x minus 3, which then when you take the derivative, you get 30x squared minus 54x plus 20. Now, if we wanted to use the critical numbers or find the critical numbers, we would use the quadratic formula, or we could try factoring this. But I haven't asked you to do that here, so we'll just leave it at that. Our method number 2 is to find the derivative using this thing called the product rule. So the product rule says if you've got a function which is defined as the product of two smaller functions, the derivative will be this. It'll be the derivative of the first function times the second function plus the derivative of the second function times the first function. So if we look at the h at x that we had started with, 2x minus 3 is the first part of that, the first function, and its derivative is just 2. The second function that makes up h at x is the 5x squared minus 6x plus 1. Its derivative would be 10x minus 6. So when you find the derivative of h prime at x, or the derivative of h at x, which is h prime at x, you're going to find f prime at x times the g at x plus g prime at x times f at x. So try that, and then you can check your work on the next slide. All right, what I have here is that I should have 2, my f prime at x is 2, times the g at x, which is 5x squared minus 6x plus 1, plus the derivative of g at x was 10x minus 6 times the first function f at x, which is 2x minus 3. Which then when you expand and simplify, you end up getting the same result as we had above. Now this looks like a lot more work than method number 1, and it's true. For this particular kind of example, it is a bit more work. But there are other examples where this actually will be quicker and easier, especially when it comes to finding our critical numbers. All right, use the product rule then to differentiate h at x defined as 3x squared minus x plus 1 all squared. So you could be nice and write that trinomial out twice. You could expand and simplify it and then do the derivative. But what I'm suggesting here is to use the product rule on it. So be nice, write it out twice, but don't actually expand and simplify. You're going to have two functions that are identical to each other. They both will be 3x squared minus x plus 1. So try that, see what you can come up with, and check it on the next part. All right, so when I did this, my derivative of the smaller function is 6x minus 1. So the derivative of the first times the second plus the derivative of the second times the first gives me the answer I have here. And then I actually have factored that using the fact that I have 2 of these 6x minus 1s times 3x squared minus x plus 1s. So this is factored form that we have, and that helps us determine those critical numbers. Now you'll notice this really didn't take very long in terms of the number of lines for the solution. And if you would have expanded and simplified, you would have had a few more terms there, and you probably wouldn't have had the factored form, which is much harder to find once you have the standard form of it. All right, let's look at the next example here. We have f at x equaling the square root of x times 2 take away 3x. So you can see we have two smaller functions making up f at x. You might want to rewrite that square root of x as another possible, or in another possible way, to be able to take its derivative like you would have earlier. But try that one, see what you can come up with, and check your work on the next slide. All right, so I rewrote the square root of x as x to the 1/2 And then when I take the derivative of x to the 1/2, I get a half x to the negative a half. And the derivative of the 2 minus 3x is just minus 3. So the derivative of the first times the second plus the derivative of the second times the first. And then I'm going to write that in its factored form in case I need the critical numbers for it. So when I factor, I notice both terms have an x in them. We always pull out the smallest power of x when we common factor. So x to the negative 1/2 is smaller than x to the positive 1/2, so I'm common factoring that out. I'm also going to take out the fraction on it because then I can write it in a rational form. When I common factor a half x to the negative a half out, I'm left with a 2x minus 3, a minus 6, and with an x. If you were to expand that through, you should see that you get this same line as we started with above. And then the 1/2, I'm going to slide the denominator onto the bottom. The x to the negative 1/2, I slide down to the bottom and make it x to the positive 1/2. And what's in the big square brackets simplifies to be 2 take away 9x. The last step was just rewriting the x to the 1/2 as the square root of x so that it matches the form of the original equation that had the root form for our variable there. All right, now moving forward with this, I have one last, I have a couple more examples here. Part C, I have now a quotient. But a quotient could really be written as a product if I were to slide that x to the 2 up to the top and turn it into an x to the exponent negative 2 using the negative exponent rule. So that's the kind of cool thing about this. We wouldn't have had a way to be able to, well, we could have, I suppose, put the x squared into each term and then done each term individually. But I'm just going to show you here that you can, do it otherwise. Okay, so try that one, check your work on the next slide, and go from there. Okay, so I got an x to the negative 2 times 2x plus 3. The derivative of the first became negative 2x to the negative 3. The derivative of the first times the second, plus the derivative of the second is 2 times the first, which is x to the negative 2. And again, I've common factored negative 2x to the negative 3 out of each term and rewrote it with the rational form with a positive exponent. I've also made a note on the previous example about always the lowest power of x gets common factored out when x is common to all terms. Okay, so the lowest power of x gets common factored out. All right, my last example, a little bit more complicated here. It's an extension of the product rule, and I'm not even giving you a chance to try this one on your own. If your f at x is now the product of 3 smaller functions, the product rule can just be extended. So instead of just the derivative of the first times the second plus the derivative of the second times the first, it's now the derivative of the first times the second and the third plus the derivative of the second times the first and the third plus the derivative of the third times the first and the second. So basically each function needs to have its derivative taken, and it's multiplying the remaining functions that are there. And so if you had 4 smaller terms, you would have then 4 pieces to your answer, where each piece would be the product of the derivative of one of the functions times the remaining functions. And they all have to have their term. I didn't bother putting this into factored form, but hopefully that makes sense. And then you have some questions to try.